start by thanking the organizer to provide the platform for us to discuss our work in these difficult times. So the paper I'm going to present today is macroeconomic forecasting in a multi-country context. It's a joint work with Andrea, Carriero, Todd, and Massimiliano Marcellino. So before the presentation, say that usual claim applies here is that the views here in solid authors and do not reflect the views of the Federal Reserve Bank of Cleveland or Federal Reserve systems. Okay, so several papers provide evidence for modeling cross-country dependence, in the forecasting context. So there are two main approaches. The first one is the VRX type of models, which means that once you have a domestic country VR and you augment foreign information after the lags of the domestic variables. The popular approach here is a global vector regressions, where you construct the foreign variables by cross-sectional average of the foreign variables using trade flows as weights. The second approach is a multi-country VR models or panel vector regressions, where all the variables in different countries are jointly modeled. And in a domestic setting, there are two features which have been found to be very useful to improve the forecasting performance. The first one is you have a larger domestic data set, and the second one is to modeling the time variation, the volatilities of the macro series. So motivated by the previous findings, so in this paper, we try to ask and answer the following empirical questions. So the first one is, does a larger domestic data set help? So mostly the papers are focused on the US data, but we want to investigate whether enlarging domestic data set is useful for other countries. And in the multi-country context, to enlarge the domestic data set, there are two main ways. The first one is to introduce more domestic variables, and the second one is you are in the small single country VR, but you have more variables from foreign countries. And the second one is, if we find that the larger domestic data set improves forecasting accuracy, can we get additional benefits by adding information from foreign variables? So to introduce foreign information, as I said before, there are mainly two approaches. The first one is the VRX type of models, and the second one is multi-country VRs. Inside the multi-country VRs, you know that to have a better forecasting performance in the larger dimension models, you have to perform shrinkage. Then the question is how to perform shrinkage. You can simply do it by treat this multi-country VR as a large unrestricted VR and use priors to perform shrinkage. Or what you can do is to impose a particular hierarchical factor structure on the unrestricted model parameter space. And I will define all of these things later. So this is what we do in this paper. So we examine how both point and density forecast accuracy is affected by different model specification choices. So all these models are in our benchmark specification, and they all include stochastic volatility. So there are three types of models. The one is country-specific model with different types of data sets. And the second one is inside the country-specific model, you augment foreign information by either factor-augmented country VRs or using global vector regressions. A third one is simply the multi-country VRs, where all the variables are jointly modeled, and you perform shrinkage either by factor shrinkage or by Bayesian shrinkage using priors. And we propose a new hierarchical shrinkage priors for multi-country VRs. But compared to the existing approaches, we find that this is more flexible than the existing alternatives. And what's more is that this flexibility will allow you to have more efficient algorithm to draw from the high dimensional VR mean coefficients, and which will also show that it's much faster than the common approach. So our results cover two data sets. So here, due to the time constraints, I will mainly talk about the fast results from the first G7 country data set, where we have 17 to 19 variables per country. It's a quarterly data set covering from the period 1983, the first quarter, to 2017, the fourth quarter. And our target variables are output growth and inflation. Okay? So the preview of our findings is that the general message we can give is that modeling cross-country interactions gives you additional gains once we have a larger domestic data set. This is particularly true when you forecast output growth. So, but we find that a substantial amount of gains, especially for density forecasts, already achieved by you inside the single country VRs. You move from 3 variable VR to 7 variable VRs. If you have larger dimension, you get additional benefits, but the amount of gains are relatively smaller than this case from 3 variables, 7 variables. So in general, across countries, adding foreign information will give you additional benefits, and we find that our new shrinkage prior yields the best forecasting performance in some cases, especially for output growth and for inflation at short horizons, I mean for up to 6 steps ahead. Country-specific VRS type of models with a different way in the multi-country we are forecasting, and may not be the best, but they generate less forecast dispersion across different countries. And we also conduct the model evaluation performance over time, and basically we find that the gains from larger models are mainly from the crisis and post-crisis evaluation period. Okay. This is a roadmap. I'll first introduce the models and estimation algorithm, and brief introduction for the data set and empirical result, then concludes. So this is our model. So in the multi-country setting where you have in a YIT, where domestic variables in country I, it will allow it to interact with variables in other countries. And we assume that the model contains stochastic volatility, where stochastic volatility has a cholistic type form, where the A matrix is all over triangular with diagonal elements equal to 1. And the stochastic volatility evolves as a random walk, and which is standard in the macroeconomic literature, we assume that this covariance matrix is full. Okay. So by shutting down the interactions across different countries, and also assume that the arrow terms are not correlated cross-sectionally, and we'll get a country-specific VR types of models. And we'll use the standard Minnesota type priors to estimate this model. So as all the data are transformed into growth rates, so the prior means always set to 0. And the hyperparameters in Minnesota prior, we use the standard setting for overall shrinkage, cross-variable shrinkage, and for the intercept, we use a non-informative prior. And for free elements in A, we also use a non-informative prior. And for the error covariance matrix and volatility innovation, we use a type prior for that. Okay. And in the country-specific model, we consider both small, which is our benchmark with 3 variables, and also medium size, where we have 7 variables, and large data set where we have 17 to 19 variables for each country. Okay. Inside the country-specific VR models, and this model can be easily extended to allow for cross-country correlation by augmenting information from foreign countries. So first, we'll first look at the factor augmented vector regressions, where you have factors in the measurement equation, where these factors are abstracted from all of the foreign variables, where the factors are estimated by principal components. For this model, we'll consider both the medium data set and large data set in this domestic YIT. And for the factors, we always extract it from the larger data set, where we stack all the foreign larger data set for each country and stack all these variables together, and we estimate the principal component by factors by principal component. So the priors are essentially the same as before, except for the fact that we specify a tied prior for the loadings for those factors. Okay. Because by setting the overall shrinkage parameters at the half of the original lambda 1, here I wrote lambda 1 star here, okay? So the factor dynamic equations are estimated by diffuse priors following the literature by Kuban-Korovelis and Pedonuzzo. And the factors in a standard way as in Banner in the 2002 Econometrics paper. Okay. Alternatively, you can introduce cross-country correlations by global vector regressions. And for standard global vector regressions, you also augmented for information like what we do for the VRF model, but instead of factors, you constructed foreign variables by cross-sectional average from the foreign by the trade weights and average all the foreign variables. And the first step is actually to estimate a country-specific model, and then after you estimate all the country-specific models and you stake all the country-specific model together to form a global model, then which you will use these type of models to do forecasting. But what we find is that the results can be very sensitive to the choice of hyperparameter values in the Minnesota prior. Basically, if you want to have a better forecasting performance, you have to specify a very, very tight prior in the global vector regressions. Okay. The last model I want to talk about is the multi-country VR models. You want to work with the unrestricted model directly because it's very general and incorporate complex dynamic structure for each variable. But the problem is that the dimension can be very high and you need to perform shrinkage. And we will consider two types of shrinkage. One is use priors, and the other one is by factor shrinkage, which I will define later. And unrestricted VRs is just simply treated as a large VR and perform shrinkage with priors. If we use Minnesota prior, this will be the same as the country-specific VRs, except that now we have a much larger dimension. And the priors are essentially the same, except the fact that for the overall shrinkage parameter, we use very small values compared to the small dimensional models, okay? For this type of models, we always combine the 7 variable domestic data set in each country. So overall, we will have 49 variables for this type of models. Minnesota type of priors is very popular and useful, but the problem is that parameter uncertainty issues are involved because the local shrinkage parameter you set it as by running the AR1 regression for each series, right? And the second issue here is that it's not approximate in multi-country setting because the paper by Econometrics and Carriero, they have shown that there are certain interesting restrictions here in multi-country VR models. Let us consider by this matrix BL. So the domestic block are essentially in the interactions between the legs of the domestic variables, right? So the off-diagonal elements are essentially the interaction between legs of the foreign variables. So here we are mainly interested in two types of restrictions. The first one is cross-sectional heterogeneity, where any domestic block is the diagonal blocks here are essentially the same for some leg lengths. The second one is dynamic interdependence. We want to check whether off-diagonal block elements are 0 or not. Okay. If you check all these parameters together with associated restrictions, and it turns out that Kuban-Korovelis proposed what is called the stochastic model specification search prior, S4 prior, to search both of the restrictions. But there are problems. The first one is that it will only have a single actually there is a hyperparameter to control the degree of shrinkage, which might be restrictive because in this spike and slab setting, once you fall into some component, there will be a very single, only one single hyperparameter to control for all the coefficients in this block. The second one is mainly computational because if you want to check the CSH restrictions, it means that in the posterior, it will be non-regular, which prevents us to use any efficient algorithm which have been developed so far. So in this paper, we propose an alternative ways to search for restrictions by using hierarchical shrinkage priors. So if you collect all the coefficients related to different blocks together and assume that it has a double gamma structure, and also even the free elements in A, you also assume this type of double gamma structure, and there is a bit global shrinkage parameter controlling for the overall shrinkage. For example, if you are in the CSH restrictions, and if the global shrinkage parameter goes to 0, which means that all this domestic part will be the same, right? Because they will be centered at 0. Okay. And it turns out that specification here in 7 and 8 are very general and nest some interesting other interesting shrinkage priors, which we'll formally show in the paper in our proposition 1. It's the links between other shrinkage priors. Okay. We also derived the marginal data density of these priors, and turns out it's just a rescaled version of the beta 2 density. And there are 3 parameters controlling the marginal distribution, where we have lambda, C, and kappa. And we will put priors to infer from these values. Okay, so the priors are basically standard in the literature, where you have exponential and gamma and inverse gamma. Sorry. And we all set it to be non-informative. Okay. And the last one is factor shrinkage, which is very popular in the early generation of this type of panel VR literature. By priori assume that unrestricted model parameters can be decomposed into a factor structure, where factors are user specific. It can be one global factor and another factors related to variable specific and country specific and also lag specific. And our empirical results, we find that the results also very sensitive to the choice of the factorizations and also have big differences between different countries. Okay? So a summary of our competing models, and we'll have 3 types of models. And country-specific model, we have with different types of data set with different dimension. And for the country-specific VRX models, we have either CIF-FAVA with those medium-sized data set and large data set. For the multi-country VRs, basically have 2 things, the Minnesota prior and hierarchical shrinkage priors. So estimation outline. So since it's a Bayesian VR, we always estimate the model by macro-chain Monte Carlo methods. And the mean coefficient are estimated by triangular algorithm developed by Carriero, Todd, and Marcellino in a 2009 Journal of Econometrics paper. And because our model dimension here can be very high if we have the 40 variable multi-country VR models. So it turns out that a more efficient algorithm exists if the dimension is larger than the sample size of the time series in the time series dimension. And we show that how the Bhattacharya 2016 paper's efficient algorithm can be adapted to our setting where you have a multivariate model, because we have VR model with different variables and with stochastic volatility. And we formally show that how this algorithm can be applied here, and we have an example on how much gains you will get if you use this type of new fast sampling algorithms. Okay, so data issues. As I have explained before, that we will mainly focus on the G7 countries data set with 3 key variables with output growth and inflation, and 3 types of data set in each country. So the small data set, 7 variables, which the variables we choose is mainly driven by the DSG models of Smith and Waters in 2007 American Economic Review. And also have a larger data set where we have 17 to 19 variables, and we have additional 14 to 16 variables, which mainly collected from the data stream. So that are the quarterly, and we only have 140 observations, which is a fairly small sample size. So, okay, so the forecasting metrics, so we will evaluate both point and density.
You have around 10 minutes left.
Okay, very
sorry for interrupting, thanks.
No worries. We evaluate both point and density forecast, And because we're using independent normalization time priors, you know that the optimal H7 head forecasts are not available in closed form, and then it means that we need predictive simulation. And point forecast we define as the median of the predictive density. And our evaluation period are from 2002 to 2017. We have 12 quarters ahead, okay? So a brief summary of our results. So enlarging the single country information set is quite useful, which is especially true for forecasting output growth and point forecast for inflation. For output growth, we find that multi-country VR models outperform both the country-specific VRs and VRX type of models in terms of both point and density forecasts. And our newly proposed priors are often the best in some cases, especially for the output growth for the densities and for the inflation, also for point and density forecasts at short horizons. So this is a table with basically we sum up the number of cases when one model becomes the best. So upper panel is for the output growth and the bottom panel is for the inflation. As you can see here, our newly proposed prior for the output growth are best in, has the most wins for the output growth, especially at longer horizons for the densities. And for the point forecast for all horizons is all comparable with the standard Minnesota time price. But some different story emerges if you look at the inflation. Especially at longer horizons, we find not so promising results because the single country benchmark models can hardly be beaten. At short horizons, we find that newly proposed priors have almost the same wins as the benchmark model. But in the longer horizons, definitely is dominated by the benchmark. And for the Minnesota type prior for inflation, as you can see here, it has the best wins for point forecast, but unfortunately for the density forecast, it performs very poorly, which means that a large predictive uncertainty around your point forecast. Okay. So I have commented everything here. Okay, so we can move on to some details. First, as I said before, is that we find that substantial amount of gains when you move from the benchmark model to the 7 variable country-specific models. Adding more variables will get additional benefits, but the amount of gains are relatively smaller. So in general, incorporating for information are useful, especially at short horizon, because as we have seen that it's not very good when you consider inflation forecasting at longer horizons. And the Minnesota time priors perform very poorly for inflation. We obtain similar findings from the annual data set. Panel restrictions are helpful. Factor shrinkage is very sensitive to the choice. Let me show you the graph here. So this is the graph for the relative percentage gains in terms of IMSFE. Here is IMSV for output growth and the log straw for output growth and IMSV for the inflation and also log straw for the inflation. As you can see, if you use the standard factor, you choose the factors, one global factor, one country specific, variable specific, and lag specific factor, and you find that it's not very good, especially for the inflation, especially and for the output growth, you find here, and for US, it can be 500% worse than the benchmark. But if you change slightly for the factorization, you can get a totally different picture of the forecasting performance, where you don't have such bad performance for US, for output growth, but unfortunately, the inflation does not get you do not get very good results. For the GVL approach, if we use the same hyperparameters as in the country-specific setting, again, we get very bad forecasting performance with 3 times worse than the benchmark. For the inflation, we have 5 times worse than the benchmark. But if we use very tight priors, and you can see here is that it gets much better, okay? And the new shrinkage prior, as you can see here, the double gamma prior, you get good results for output growth, but not for inflation. For output growth, you mainly, for most of the countries, you get gains, except for the Japan, but not for the inflation here. Okay. We also conduct a model evaluation of performance over time and specify this is the evolution of cumulative sums of the IMS FE, and this is for the log score. As you can see here, that is very difficult to get accurate forecast for the output growth during the crisis period. And for the density forecast, it's only the same. And we find that the larger models, for example, let's take the blue line as example. You can see here is that it's mainly from after crisis period and dominated by other models, which means that larger dimensions is very useful for forecasting output growth, and again, so mainly from the post-crisis and post-crisis period. For the inflation, we find that except for the very inferior performance for the mini-swap type prior in terms of density forecast, basically for all the other type of models, the performance are very, very similar across time. Okay, so to conclude. So in this paper, we assess the several issues in multi-country macroeconomic forecasting. We consider three types of models: country-specific models, country-specific models augmented with foreign information, and multi-country VERs. Our empirical results show that once you have a larger domestic data set, it's also very useful if you introduce foreign information to your model. And we find that the gains from large dimension are mainly from the crisis and the post-crisis evaluation period. And this is particularly true for output growth. Okay, that's it, thanks.
Great, thank you.
I'm done.
Okay. We do have a little bit of time if there are any questions.
Okay. Can I ask something?
Okay.
My question is about the assumption on the stochastic volatility process.
Okay.
Is that AR1 or is a random walk? Because it seems to be pretty important to get the density forecasting